Hi, it's Miss Murphy again. Uh, I'm doing this video for my sweet teacher friend, Miss Silber. This will cover half-lives and radioactive decay. I'm going to pause the meeting, the recording, and I'll be back in a minute with my iPad. Okay. Uh, okay. So we're back. I'm going to try to do this, make this short and sweet. Okay. We are talking about half-lives and radioactive decay. Let's talk about half-lives first. This is simply the amount of time, all right, period of time it takes for one half of a radioactive isotope to decay. Okay. So what is a radioactive isotope? A radioactive isotope is an unstable substance. All right. What is the substance? It's an isotope. It's some type of element which has a nucleus with too much stuff in it. Right. We can imagine a sample of atoms, say of uranium, is common here. And it's unstable. Well, because it's unstable, it decays, right? It decays. In the process of decaying, it loses half of its mass, right? And this period of time it takes for this initial original substance to decay, and in the process, giving off radiation, right? Why is the substance decaying? Because it's unstable. It's unstable, therefore it decays. As it decays, it loses half of its mass, right? We see that we have half. So if this weighed 100 grams, this would weigh 50 grams, all right? The half life is the amount of time it takes for 100 grams of this substance to cut in half, right? The process, it decays. In the process of decaying, it gives off radiation. And at the end of that process, one half of the substance will remain, one half of its original mass, right? One half of the number of original isotopes. All right. So we're going to be talking about the half-life, how long it takes to get from the beginning to the end, how much radiation is giving off in the period of time. That radiation will be measured in curies, all right? That is a unit of radiation. So we'll see values that are mass values. We'll see mass values that are numbers of half-lives. We'll see how many curies, or we'll be given curies. And we'll have to do some calculations. All right, so let's go. Our first example problem, half-life practice problem number 1. With a radioactivity level of 100 curies. What does that mean? That means that one half-life, right, whatever period of time that is, releases, 100 curies of radiation. All right. So every time this particular substance undergoes a half-life, 100 curies of radiation is released, if that makes more sense to you. We see that a half-life is 50 years. One half-life occurs every 50 years. We are asked what will be the radioactivity level. That means how many curies, right? How much radiation released. And then they tell us that the total time is 200 years. All right. Oops, a little too many S's there. So we've had 200 years of time. Every 50 years is a half-life. Every half-life, we release 100 curies. How many curies have been released? And we can make sense of this if you haven't already. I'll show you. Let's start at 0 years. All right. And let's let 50 years pass because that's our half-life. And after 0 years, 50 years has passed. We're at 50 years. After another 50 years, which is another half-life, right? Every 50 years is a half-life. Well, that takes us to 100 years, right? And then another 50 years goes by, right? A whole nother 50 years. And it's been a total of 150 years now. And at this point, we've had 1, 2, 3 half-lives. But we're not yet to 200 years, like the question is asked. But we can see that after another 50 years has gone by, we are now at 200 years. So 200 years of time has gone by. And during that period of time, we could see that we've had 1, 2, 3, and 4 half-lives. 4 half-lives has gone by. And the question said, well, how many curies were released if 4 half-lives has gone by? Well, I can look up here and see that each half-life is 100 curies, right? This half-life released 100 curies. 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 Oops, I forgot my 100, didn't I? So we can easily see now that there were 1, 2, 3, 400 curies released in this period of time, right? You may have, if you had me for chemistry, seen that they gave us years, they asked for curies, and they gave us 2 ratios to use, right? And I would be in class and I would say, what do we always start with? And you would say, we start with what's given. So we would start with what's given. Let's do that real quick. 200 years. Let's convert our years to half-lives, right? And we see that that's 50 years for every 1 half-life. And now let's convert our half-lives to curies. 1 half-life, 100 curies. Cross off your units, you're left with curies. Your answer is curies. 200 times 1 times 100, 200, 20,000 divided by 50 times 1, and that equals, once again, 400 curies. So you have 2 ways to do that. I'm going to proceed since you can rewind if you need to. Let's look at another one. I think it's just the same. I would encourage you to pause, do it yourself, see, and then watch this and see if you get the same answer, okay? So right now you're going to pause and you're going to do it and you'll come back and I'll go. So radioactivity level 1 half-life equals 500 curies. 1 half-life equals 30 years. How many curies in 150 years? I will draw it out for you again. 150 years has gone by. Every 30 years we have a half-life. So if I start at 0 years, at year 30, we've had 1 half-life. Add 30, I get to year 60. We've had 2 half-lives. Add 30, I get to year 90. We've had 3 half-lives. Add 30, I get to year 120. We've had 4 half-lives. Add 30, I get to year 150. We've had 5 half-lives. All right. Each half-life releases 500 curies. 500 curies, 500 curies, 500 curies. You see where we're going here. Oops. Forgot the number. 500 curies, 500 curies, 1,000, 1,000, 500. So 2,500 curies, right? No calculators needed here. We can do that easily on our own. All right, if you were to do the dimensional analysis here, we would start with the unit we were given, 150 years, right? We would convert years to half-lives, 30 years, 1 half-life. We would convert half-lives to curies, 500 curies, 1 half-life. 150 times 500 divided by 30. I'm pretty sure you'll get the 2,500 curies. Okay. I'll continue. Rewind, do it again if you need to. Ask questions. Okay, this one's going to come a little bit different. The half-life of plutonium, 239. This number is not important in terms of solving the problem. It is simply part of the name of the radioactive isotope, right? It's part of his name. What is important is this. It's been 24,300 years is the half-life, right? That's a long half-life, right? So this guy doesn't go away. He stays around. Nuclear bomb released 8 kilograms of the plutonium-239. And we want to know how many years, question mark, time, years, will pass before we get to a final mass of 1 kilogram. Okay, so what's the deal here? We have 8 kilograms and it's unstable and it will therefore decay, and it will decay in half-lives. All right, and we want to know after it decays how much time will have gone by. All right, how many years would pass before the amount is reduced to? All right, so we're going to start with our 8 kilograms and we are going to cut it down 1 half-life, right? 1 half-life. And after that 1 half-life, half of it would remain. So I'll cut that in half and I'll have 4 kilograms. And then I'll have another half-life because I need to go from 8 all the way to 1, right? We want to know how long that takes. Well, after this half-life, I started with 4 grams. So 2 kilograms will remain. That was a half-life. I now have 2 kilograms. It's going to decay. It will lose 1/2 of its mass. So half of 2 will remain. And that will be another half-life, right? So we started with 8. That's what they gave us. We ended with 1. That's what they asked. And then they want to know how many years was that. Well, we see that we've had 1, 2, 3 half-lives. That doesn't answer the question and wants to know how many years. So we see that each half-life of plutonium, each time it cut in half, it took 24,300 years, right? So this process took this long for it to go from 8 to 4. And then the 4 decayed to 2, right? It had to cut itself in half. That took this long. The 2 had to turn into 1. That took this long, right? So if we take those and we add them together or multiply them by 3, we should get our answer. And then you can do that if you want to. We could also utilize that with, no, we can't use a t-chart with that one because of the nature of this exponential decay here. So that's not going to work. You're going to have to do this like this, or that's the easiest way. Last one. We are doing the same thing, but this time we have a graph. All right. Whenever you see half-life graphs, they'll always take this same shape. You'll see this exponential curve, right? Because we have an exponential decay here. Notice this is how much remains, and this is how long it is taken for a certain amount to decay to another amount. All right. So I'm going to clean that up, and let's look at the data that we have and the question that we're being asked. We're talking about magnesium 28. Once again, that 28 is not important. It's the substance that is decaying. We are to, look at the graph and determine the half-life. All right, well, check it out. What you're going to do is you're just going to look at how much you start with. Oops. Hold on. All right, we start with 1 here. So whatever that number is how much I'm going to start with. And then I ask how many grams will remain after 1 half-life. Well, whatever this number is, and let me get rid of that because nothing says kilograms, but it says 1 fraction remains. The whole thing is there. Well, after 1 half-life, what amount will remain? Half. Yeah, right, half. So if I take the original number, the 1, and I cut it in half, that takes me to 0.5. Well, now I just need to read my graph. I went from 1 to 0.5 in 20 years. So the half-life of magnesium 28 is, 20 years. That's simple, right? Just take the original value, cut it in half, read over, read down, and you've got your half-life. All right. I've enjoyed this. I hope that you have too. I will now be ending this meeting.